Okay, good morning, dear students. So, today in this lecture, we will discuss about the eigenvalues. It is a very important chapter in linear algebra. So, first we need to understand about the basic concept of the eigenvalues. Students, basically, eigenvalues is a set of scalars that associated with is a set of scalar that associated with a set of linear equation. This is the meaning of LE is linear equation, most probably in matrix equation. So this is a basic concept related to the eigenvalue. Students, basically the eigenvalue is a German word. It is a German word. It is a German word, and the meaning of this word is the meaning of the eigenvalue is the characteristic. The meaning of the eigen is characteristic. So we can say that the meaning of the eigenvalue is eigen is characteristic. Characteristic. According this name, we can call the eigenvalues. We can say the eigenvalues by the different names like characteristic equation, characteristic value, characteristic value, like we can call it the characteristic root, characteristic root, we can call it proper root, proper values, we can call it latent root. Okay, and basically eigenvalue is useful in linear transformation. The application of the eigenvalue is it is useful in linear transformation. It is useful in linear transformation, or we can say it is used in linear transformation. For example, suppose that we have a negative eigenvalue. It's mean the direction of the transformation is negative. Okay, suppose that we have a negative eigenvalue, then the direction of the transformation is negative. And if we have a positive eigenvalue, then the direction of the transformation is positive. So it is very clear concept of the eigenvalue. That is, eigenvalue is useful in linear transformation. Now, how can we calculate the eigenvalue? For the calculation of the eigenvalue, we need a eigenequation. We need a eigenequation. Eigenequation. Students, eigenequation is an equation in which we have a square matrix X A with a vector X and equal to lambda X, where lambda is a scalar. Lambda is a scalar which is known as eigenvalue and X is an eigenvector of matrix A corresponding to eigenvalue lambda. And suppose that this is a square matrix, we can say that A equal to Aij n cross n, because this is a square matrix. X is an eigenvector of matrix A. This is X is an eigenvector of matrix A. Vector of matrix A. X is an eigenvector of matrix A corresponding to eigenvalue lambda. We have a very interesting concept related to the eigenvector and eigenvalue. There could be infinitely many eigenvectors corresponding to one eigenvalue. If we have a one eigenvalue, then there could be infinitely many eigenvector corresponding to the eigenvalue. Now, our target is to find the eigenvalue. So students, first we need to write this equation in this form: ax minus lambda x equal to 0. We can take it in left hand side, and when we take x is common, then a minus lambda and x equal to 0. This is the eigenvector. Always remember a very important thing: 0 vector is not an eigenvector. 0 vector is not an eigenvector. 0 vector is not an eigenvector. Okay, because it is a point. Suppose that we have a vector like 0, 0. Then this is a point in 2-dimensional axis, origin in 2 dimensions. This is a origin in 3-dimensional axis. So 0 is not an eigenvector here. It's mean, according the multiplication rule, suppose that we have two values a and b equal to 0. Then the case is either a equal to 0 or b not equal to 0. A not equal to 0 or b equal to 0, or either both is equal to 0. So here this is not equal to 0. It's mean this value equal to 0. A minus lambda equal to 0. Now we have a very interesting logic related to the subtraction of a scalar from a matrix. It is not possible to subtract a scalar from a matrix without multiplication of an identity matrix with the scalar. Okay. For example, suppose that we have a matrix 1, 2, 3, 4. Then it is not possible any scalar. Suppose 5 is a constant here. Then it is not possible to subtract a constant or a scalar from a matrix directly. For the subtraction of a scalar or a matrix or a constant, first we need to put identity matrix of the same order with the matrix. So for subtraction of this, we need to write a identity matrix of the same order, like the order of A with this. Then we can take the determinant of this value. This is known as eigen equation, or this is known as CR equation, characteristic equation. And this equation is totally responsible for finding the eigenvalue. This is the characteristic equation. Okay, and the solution of the characteristic equation is known as eigenvalues. Okay, so this the solution of this equation is known as eigenvalue. Is it clear? Let us take an example for finding the eigenvalue. Suppose that we have a matrix A, and matrix A equal to 4, 2, 3 and 5. This is a matrix A, and we want to find the eigenvalue of this matrix A. Then first we need to put this value here in place of A. A is 4, 2, 3 and 5. minus lambda is the eigenvalue, and we need a same order matrix, identity matrix here. It is equal to 0. Now we can simplify this value. Then the simplification of this value is when we subtract, this is 4, 2, 3 and 5. Students, when you multiply a scalar with a matrix, then the scalar multiply with each and every element of the matrix. So this is multiply with lambda 1, then it is lambda 0, 0 and lambda. It is equal to 0. Now subtract this value, 4 minus lambda, this is 0, 3 and 5 minus lambda, this value equal to 0, and the determinant of this matrix. Now find the determinant of this matrix. We can multiply this with this, 4 minus lambda, 5 minus lambda and minus 6, it is equal to 0. Okay. Students, you can learn the properties of the determinant and about the determinant in my previous lecture, in my previous video lectures. Now simplify this condition. This is 20 minus 4 lambda minus 5 lambda plus lambda square minus 6 equal to 0. Then lambda square minus 9 lambda, this is 9 lambda, and plus 14, it is equal to 0. Now you can simplify this. We have the many method for simplification of a quadratic equation. One of them is middle term factorization method. It is applicable when we have a middle term such as we can factorize the middle term such as the multiplication of the factor equal to the last term, this is the last term, and summation and subtraction of the factor equal to the middle term, this is the first method. We have the other methods like the Sridharacharya formula for finding the answer of the such type question. So we can factor this, we can find the factor 7 plus 2 9 and 7 into 2 14 equal to 0. Then lambda square minus 7 lambda minus 2 lambda minus plus 14 equal to 0. Then lambda is common, lambda minus 7 minus 2 is common, lambda minus 7, it is equal to 0. We can take lambda minus 7 common, this is the lambda minus 2 equal to 0. You can simplify this when you put this is equal to 0. Then lambda equal to 7 is the first eigenvalue and lambda equal to 2 is the second eigenvalue here. So students, we have two eigenvalues of this matrix because the order of the matrix is 2 into 2. Now we have some important properties of the matrix algebra. First property is, suppose that we have a matrix of order n into n. For matrix A equal to Aij n into n. Okay. For matrix A equal to Aij n into n, there is always n eigenvalues exist, or we can say that this matrix possesses n eigenvalues. Okay, that is the total number of eigenvalues. Total number of eigenvalues are n. Okay, or we can say that we have n eigenvalues for this matrix because the order of this matrix is n into n. This is the first property. Now second property, suppose that we have a singular matrix. For a singular matrix, singular matrix means a matrix in which determinant of the matrix equal to 0. This is a singular matrix. So for a singular matrix, always there exists at least one zero eigenvalue. For a singular matrix, always there exists one, at least one, always matrix exists at least, matrix exists at least one zero eigenvalue, zero eigenvalue. Okay, for example, suppose that this is a matrix 0, suppose that this is a matrix 1 2 and 1 2. This is a matrix, so the determinant of this matrix is 0. You can directly understand about it. Determinant of this is equal to 0. Now if you want to find the eigenvalues of this matrix, then A minus lambda equal to 0. It's mean you have A is 1 2 and 1 2 minus lambda eta is 1 0 0 1. This value equal to 0. You can subtract, then this is equal to 1 minus lambda 2, and this is the 1 minus 0 is 1, and 2 minus lambda. Now you can find the determinant of this value. 1 minus lambda 2 minus lambda minus 2 equal to 0. This is implies 2 minus lambda minus 2 lambda plus lambda square minus 2 equal to 0. Lambda square minus 3 lambda, and this value you can cancel out. This is equal to 0. Now take the lambda common. Lambda minus 3, it is equal to 0. Lambda equal to 0 and lambda equal to 3. So there is one eigenvalue is 0. So the property is, if you have the singular matrix, then at least one eigenvalue of the matrix is equal to 0. It is a property. We have more than one eigenvalues of the matrix equal to 0, but the necessary condition is at least one eigenvalue of the matrix is 0 if you have a singular matrix. Then third property is, if you have a non-singular matrix, this is a non-singular matrix which determinant is completely equal to not equal to 0, then always all the eigenvalues are non-zero. All the eigenvalues are non-zero. Okay, we can say that all eigenvalues of matrix A not equal to 0. Now the fourth property. Suppose that we have a matrix A. If A equal to Aij is a matrix of order n into n, then the eigenvalues of this matrix, the eigenvalues are lambda 1, lambda 2, lambda 3 and dot dot so on lambda n, because this is an n cross n matrix, so we have n eigenvalues of this matrix. Students, if you want to multiply a scalar with this matrix A lambda, A with the matrix A, suppose we want to multiply a scalar with this matrix A, then always the eigenvalues of matrix A is A lambda 1, A lambda 2, A lambda 3, A lambda 4 and A lambda n. Clear? So the eigenvalues of AA is A lambda 1, A lambda 2 and dot dot so on A lambda n. Students, the scalar automatically multiplied with each and every eigenvalue of the matrix So you don't need to calculate the eigenvalue of A. For example, suppose that we have a matrix A equal to alpha, beta, gamma and delta, and suppose the eigenvalues of this matrix is lambda 1 equal to P and lambda 2 equal to Q. Then the eigenvalue of the 7A, because when you multiply the 7 with this matrix, then this is alpha, beta, gamma and delta. This is equal to 7 alpha, 7 beta, 7 gamma and 7 delta. Then the eigenvalues of this matrix 7A is 7P and 7Q. It's mean you can directly multiply that scalar with the eigenvalues of the input matrix. This is the input matrix, and we multiply 7 with this matrix, then this matrix convert into the new matrix. So you don't need to calculate the eigenvalues of the new matrix after multiplying a scalar. You can directly find the eigenvalue with the multiplication of the eigenvalues of the previous matrix with the such type scalar. Okay. Now the next property, this is B property, this is the 4B property. Students, suppose that we want to find the nth power of the matrix A. The eigenvalues of A to the power n is lambda 1 to the power n, lambda 2 to the power n, lambda 3 to the power n, and dot dot so on lambda n to the power n. It is very simple. A to the power n means when you take the nth power of a matrix, then we don't need to calculate the eigenvalue of the nth power. It is just the nth power of the eigenvalue of A. For example, suppose that you have a matrix A. This is a matrix A, alpha, beta, gamma and delta, and the eigenvalues of this matrix lambda 1 equal to P and lambda 2 equal to Q, and we want to find the cube of this matrix. Okay, then it is equal to alpha, beta, gamma and delta to the power 3. Then you can directly find the eigenvalue of this matrix. The eigenvalue of this matrix is because this is a third cube, this is the cube of this matrix. So the eigenvalue of this matrix is lambda 1 equal to P to the power 3 and lambda 2 is P to the power Q to the power 3. So you directly take the power, similar power to the eigenvalue of the matrix with respect to the matrix. Okay, it is very simple. This is a matrix, and we have the eigenvalue of the matrix, and this is the cube of the matrix. Now the eigenvalue of the cube of the matrix is the cube of the eigenvalue of the previous matrix. So it is very easy. Okay, you don't need to calculate the eigenvalue of this matrix. So this is the third property, property B of 4B. Now the last, this is the C property of third property of the 4B. The eigenvalue of the inverse of a matrix is equal to the eigenvalues of A inverse equal to the eigenvalues of A inverse equal to lambda 1 to the inverse, lambda 2 to the inverse, and dot so on lambda n to the inverse. It is very easy. Again, you can take the inverse of the eigenvalues. Similarly, in this above example, suppose that you want to find the eigenvalue of the inverse of this matrix. Then the eigenvalue of the inverse of this matrix is lambda 1 to the power P to the power minus 1 and lambda 2 to the power Q to the power minus 1, inverse of the eigenvalues. It is very easy. Now the last property, it is very important. The last property is the eigenvalue the eigenvalues of A, matrix A and A transpose, the transpose of matrix A. Okay, the eigenvalue of matrix A and its transpose are same. That is, suppose that you have a matrix A 4, 5, 6, 7. Okay, and suppose the eigenvalues of this matrix are lambda 1, lambda 2, and its transpose is A transpose. It is equal to 4, 5, 6, 7. Again, the eigenvalues of this matrix are lambda 1 and lambda 2. It is very simple. Okay. So these are the some properties of the eigenvalue. Students, you can easily calculate the eigenvalue with the help of this equation, A minus lambda I equal to 0. This is the characteristic equation. Okay. Okay, students. Thank you. Thank you to all of you. So in your next lecture, we will learn how to calculate the eigenvector with respect to the given eigenvalues, with respect to the eigenvalues of the matrix. Okay. Thank you to all of you. Thank you.